Hey everyone! Today we're diving deep into one of the most fundamental ideas in electricity. What actually causes electrical resistance? And more importantly, how we can control it. But first, let me ask you something. Have you ever wondered why the tiny, thin filament in an old light bulb glows white hot, but the thick power cord plugged into the wall stays perfectly cool? What's going on there? Well, by the end of this explainer, you are going to know the exact physics behind that. So here's our game plan. We'll start by looking inside a conductor at the microscopic level. Then we'll see how its physical shape changes things. After that, we'll build the master formula that pulls it all together, check out some real-world uses, and wrap up with a solid strategy to help you nail this topic on your exams. All right, first up, let's zoom way in, down to the atomic level. You see, resistance isn't just some random number, it's born from what's actually happening deep inside the material itself. And the first major factor we need to talk about is temperature. You know how your phone or laptop gets warm when you use it a lot? Well, you're seeing this effect in action. That heat has a direct impact on how easily electricity can get through. So let's break it down. Picture electrons trying to move through a neat, orderly grid of atoms. We call this a lattice. Now, when you heat up that wire, you're basically giving those atoms a shot of espresso. They start vibrating and shaking all over the place. For an electron trying to get through, it's like running down a hallway where the walls are suddenly shaking like crazy. The more those atoms vibrate, the more the electrons crash into them, and every single one of those collisions slows them down. That opposition to the flow, well, that's resistance. And we can see this in experiments. If you measure the resistance of a light bulb filament when it's cold, and then again when it's glowing hot, you'll find the resistance is shot way up. So the key takeaway here is simple. For most conductors, when the temperature goes up, the resistance goes up too. Okay, factor number 2, the material itself. This might seem obvious, but it is so important. A copper wire is just fundamentally different from an iron wire. The type of atoms that make up a substance determines its natural, built-in resistance. And that's because every material has its own unique atomic structure and a different amount of free electrons available to carry the current. Copper, for example, is like a superhighway for electrons. It has incredibly low resistance. Iron is more like a regular city street, a bit more traffic. And then you have alloys like nichrome, which are literally designed to be an electrical traffic jam. And we'll see in a bit why that's actually super useful. Okay, so we've covered what's happening inside the material. Now let's zoom back out and talk about the outside factors, the actual shape and size of the conductor. Let's start with a simple one. How long is the wire? Do you think making a wire longer makes it harder for current to flow or easier? Well, it turns out it makes it harder. Resistance is directly proportional to the length. Think about it like running a race. A 100-meter dash is way easier than a full marathon. Why? The longer the path, the more chances you have to get tired or stumble. It's the same for electrons. A longer wire just means a longer obstacle course of vibrating atoms to navigate. So if you double the length, you essentially double the number of potential collisions, which means you double the resistance. Now for our final factor, and this is the one that brings us right back to our original question, the thickness of the wire. In physics, we call this its cross-sectional area. With this one, the relationship is inverse. That means a thicker wire has lower resistance. And this makes perfect sense if you think about it. Imagine a crowded hallway. If it's really narrow, everybody gets jammed up, and it's hard to move. But if you suddenly open that hallway into a wide corridor, traffic flows smoothly. A thick wire is just like that wide corridor. It gives the electrons way more lanes to travel in, which reduces the overall traffic jam or resistance. And that's exactly why that thin filament gets super hot. Its high resistance causes a ton of energy to turn into heat, while the thick power cord stays cool. Okay, we've explored all the key factors: temperature, material, length, and area. Now for the really cool part. Let's combine them into one single powerful formula that you are going to use all the time. Let's build this together, step by step. We've established that resistance, R, is proportional to length, L. We also figured out that it's inversely proportional to the area, A. So if we combine those, it's logical that R is proportional to L divided by A. Now, to turn this from a proportionality into a real equation, we need to add a constant. This constant's job is to represent the material's natural, inherent resistance. We give it the Greek letter rho, and it's called resistivity. So this property, resistivity, is what we were talking about earlier. It's the number that captures the nature of the material. It's an intrinsic value. Copper will always have its specific low resistivity, and nichrome will always have its high resistivity, no matter what shape or size the wire is. We measure it in ohm meters. Now listen up, because this is an absolutely classic exam question. What is the difference between resistance and resistivity? Think of it this way. Resistivity is like the density of a substance. The density of gold is always the same, right? But the weight of a piece of gold depends on how big it is. It's the exact same idea here. The resistivity of copper is a fundamental constant for copper, but the resistance of a specific copper wire, the object, depends on how long and thick you decide to make it. And just to complete the picture, you'll sometimes hear about conductivity. It's represented by the letter sigma, and it's literally just the inverse of resistivity. So if resistivity measures how much a material resists current, conductivity measures how well it conducts it. Simple as that. Okay, now that we have our master formula, let's see how it explains why engineers pick very specific materials for very specific jobs. This is where all that theory becomes real-world technology. This table pretty much says it all. Copper has a super low resistivity, which makes it perfect for electrical wires. We want to lose as little energy as possible. Tungsten has a high resistivity and a crazy high melting point, which lets it glow white hot in a light bulb without just vaporizing. Nichrome also has high resistivity, which is perfect for things like toasters and space heaters, where the entire point is to generate a lot of heat. And then there are semiconductors, like silicon, which have a resistivity we can actually control, and that is the magic that makes all of our modern electronics possible. All right, let's switch gears and focus on what this means for you. How do you take all this knowledge and turn it into full marks on your exam? I've got a simple game plan for you. First things first, you have to nail the definitions. Know what resistance, resistivity, and conductivity mean inside and out. Second, know the proportionalities by heart. Third, memorize that formula. R equals rho L over A. Fourth, and this is a big one, be ready to clearly explain the difference between resistance and resistivity. And finally, remember those key applications we just talked about. And when you get a math problem, don't panic. This four-step method is your best friend. Step 1, write down every single value the question gives you. Step 2, write down the formula. Step 3, plug in your numbers, rearranging the formula first if you have to. And step 4, calculate the answer, and please don't forget to include the correct units. Following this structure will save you from making silly mistakes. And there you have it. We've gone from the inside of an atom all the way to a practical exam strategy, so I'll leave you with one last puzzle to think about. You now know the formula R equals rho L over A. With that in mind, how do you think a dimmer switch on a light actually works? Is it changing the length of something, the area, or maybe even the material? Give it some thought. Thanks for watching.